Hello everyone, my name is Salio. I'm from Duke University. So today I will introduce our work, CollabAR. This is an edge-assisted collaborative image recognition system for augmented reality. So this is our outline. First, I will give the introduction. Second will be the system design. Third will be the dataset that we collected. Finally, will be the evaluation part. The augmented reality is a technology that will lay out a virtual content around a user. And the image recognition will first recognize the object and help AR to lay out the corresponding content to enable the seamless contextual AR experience. However, distorted images in the real world will happen. For example, the motion blur happens because of the movement of the smartphones or the head-mounted devices. So this is a short video. We use the Magic Leap 1, the head-mounted devices. We can see there are a lot of frames contains the motion blur. And the Gaussian blur happens in the underwater foggy or defocusing scenario. And this is a short video. We use the Nokia 7.1 in the foggy scenario. And finally, the Gaussian noise happens in the low illumination conditions or with the low quality image sensors. And we also quantify the proportion of those distorted images in the real world scenario. For example, we use Nokia 7.1, take a video in the dark room condition, and find there are over 39% if frames suffer the high-level Gaussian noise effect. Similarly, over 99% images suffer the high-level motion blur in the corridor environment when using the Magic Leap 1. And the similar results will happen when referred to the Gaussian blur effect. So those multiple distortions will cause dramatic performance degradation of the deep neural network for the image recognition. We train a neural network based on the MobileNet V2 skeleton and trained it by the Caltech dataset, and find the accuracy will drop a lot when we're increasing the degradation level. To fix this problem, we design our system. Our key idea is the collaborative image recognition, which means we can leverage the temporally and spatially correlated images to improve the image recognition accuracy in heterogeneous scenarios. The temporally means that we use the images taken within a certain freshness, and spatially means that we use the images facing the same object. And the heterogeneous scenarios means that in the scenario, we have multiple distortion types and multiple distortion levels. Our system consists of the mobile client and the edge server. In our edge server, there are three main parts. First is the distortion-tolerant image recognizer. Second will be the correlated image lookup module. And third will be the multi-view ensembler. When running our system, the pose estimation will first be run on the mobile client based on the cloud anchor. And the anchor and the time steps will be sent to the anchor time cache. And our lookup module will use the information to find those correlated images and send the image IDs into the ensembler. At the same time, our images will be sent to the distortion classifier firstly, and it will assign the images to its corresponding expert. The expert will recognize the images and send the results to the ensembler. And our accelerate assisted multi-view ensembler will ensemble those results based of the correlated images and send the results to our mobile client. The first part is our distortion classifier. Our distortion classifier based on the Fourier spectrum of the original images, because different distortion type will introduce different frequency pattern in the Fourier spectrum. So we can see that the motion blur will introduce the high frequency components along the direction perpendicular to the movement path. And the Gaussian noise will introduce the high frequency components in all directions. So we use this spectrum as the feature sent to a shallow neural network and to get its distortion type. And based on the top of the distortion classifier, one of the 4 dedicated recognition experts will be selected for the image recognition. Each of those experts is a deep neural network that has been fine-tuned to recognize a specific type of distorted images. There are 3 steps. First, we will initialize the deep neural network by training it on the ImageNet dataset. Second, we will fine-tune those neural network using the pristine images to get pristine expert. And finally, we will fine-tune those pristine expert to by 15% pristine images and 15% degraded images to get the 3 different expert. And to identify the spatial correlated images, we will leverage the Google Cloud Anchor provided by the AI code as the reference for pose estimation. The anchor is a virtual identifier which will describe a fixed pose in the physical space. It can be resolved by a user to establish a common spatial reference among them. So for example, we have 2 users face the same object, and the anchor will appear in both of the user's view. So they are correlated. And the temporarily correlated means that we take the image within a certain time freshness. However, given the heterogeneity of the different images, will lead to the unequal recognition performance. To quantify their performance and help the ensembler in aggregating the results dynamically, we propose to use the normalized entropy as the accelerator feature to help the aggregating. We basically use the entropy to weight the probability vector from different experts, and the final vector will be the summation of those weighted results vectors from the correlated images. Also, there are some multi-view datasets, but either of them contains few categories or few instances, or some of them only contains the image with black background. So we collect our own dataset here with different categories, different views, different background complexity, and a different number of instances. And we also use existing distortion generating math model to augment the pristine image set and to get the distorted image set. In the evaluation part, first is the implementation. We implement the client use the Android smartphone, and the edge server use a desktop. We use the Keras on the top of TensorFlow as our deep learning framework, and the communication we use the Flex through the HTTP protocol. We use 4 benchmark datasets. 2 of them are single view datasets, and 2 of them are multi-view datasets. And the mobile distortion datasets and VMDD datasets are collected by ourselves. First, we evaluate our distortion classifier and find that they perform well on the 4 datasets, 1 real-world datasets and 3 synthesized distortion datasets. And they can achieve average 94% accuracy here. And we also test our distortion expert. We found that we implement the expert using the mobile net skeleton and the AlexNet skeleton. We found that the mobile net skeletons outperforms the AlexNet one, and the expert will be robust with the distorted images. However, we still experience a modesty accuracy drop when the distortion level is high. The accuracy drop will become more severe when the image contains multiple distortions, but it can be resolved with the help of multi-view collaboration. And for the first multi-view collaboration, we introduced the single distortion, which means there's only 1 distortion type in 1 image. And we test it on the 4 conditions, with or without the distortion classifier, with or without the accelerator features. We can see that the distortion classifier can improve the overall accuracy by 20 to 16%. And if we use the accelerate assisted feature, we can achieve the highest accuracy. And the accuracy will increase with the number of the aggregated view, nearly 100% when the number of view up to 6. And we observe the similar phenomenon when refers to the multi-distortion scenario. And we consider the 4 combination. The motion blur combines the Gaussian noise, Gaussian blur combine the Gaussian noise, Gaussian blur combine motion blur, and all the 3 types of the distortion. And with the increasing of the number of view, the accuracy will still increase. And we will consider in what conditions our accelerated ensemble learning will performs well. So the improvement is more pronounced when there are more bad views than the good views. For example, the bad view means the image contains multiple distortions with high distortion levels. And the good view means the image is a pristine image. And in this picture, we can see that if the image contains the 3 kinds of distortions, and if there is 1 good view and 3 bad view, and our methods can improve the accuracy up to 13%. And we also test our system profiling. We found that the least computational latency will be 8.1 milliseconds on the edge server, and our end-to-end latency will achieve as shown here. So we can achieve almost 13 FPS recognition speed here. And we open source our dataset. Welcome to use them, and thanks for those funding. Thanks and questions.